Okay, so for the first problem, they say a particle moves along the x-axis for t greater than or equal to 0. The position of the particle is given by x of t equals t cubed minus 9t squared minus 21t plus 6. At what time t does a particle change direction? Okay, so maybe good to kind of imagine that what's going on here. So there's a number line, and the t values could be negative for certain values, but this just to kind of get some idea of what's going on. So think about there's a particle that's just kind of moving along the number line, sometimes going left, sometimes going right. At different points in time, you can't really tell by this graph. This graph doesn't involve time. But at different points in time, this particle is going to be at different positions. Sometimes it's going to be moving to the right, which means the velocity will be positive. Sometimes it'll stop for a second, velocity 0, and then go left, that would be velocity negative. So just think about what's going on with this particle. Okay, if the particle was moving to the right and then stopped and then went to the left, then wherever it stopped would be the farthest right that it goes, at least for a little time period around there. Okay, so just getting an idea of like what's going on with some of this stuff. These types of problems. Okay, so they say, they give the position and they want to know where it changes direction. At what time does it change direction? Okay, so they want to know when a particle changes direction. We'll kind of put down here. Okay, when a particle changes direction, so that means what has to happen is the velocity has to be 0. And then the velocity has to either go from positive to negative or from negative to positive. Okay, so if it was going from positive to negative, if it was positive and then 0 and then negative, that means it would have been moving to the right, stopped, and then started moving to the left. So that changes direction. If the particle was going from, if the velocity was going from negative to positive, and this is velocity. So if the velocity was going from negative to positive, that means the velocity would have been, that means the particle would have been going to the left, so that's a negative velocity, and then 0, and then to the right, so that would have changed velocity. Okay, so in this problem, we want to see at what time does it change direction. We want to know what time the velocity is 0, and then we would have confirmed that it goes from either positive to negative or negative to positive. Okay, so let's look at the velocity. So first we'll take derivative of the position. Okay, and then we'll set this equal to 0. Alright, this one we can divide by 3. Okay, and then we'll factor. And then set each factor equal to 0. And you just get the opposite. Okay, so these are the times when the velocity is 0. Velocity 0 is t equals 7 and t equals negative 1, but the original problem says for only t values that are greater than or equal to 0. So this one we can ignore since that's negative. Okay, so now we just want to confirm that the particle did change direction, because just because a particle's velocity is 0 doesn't mean that it necessarily changed direction. So So the velocity could have been positive, so that means moving to the right, and then 0, so it stops. But then it could be positive again, and then that means it just would have kept going. So something could have go in one direction, stop, and then keep going in the same direction. And then that, even though the velocity was 0 for a moment, it didn't change direction. So one of these has to happen. Velocity has to either go from positive to negative or negative to positive. Okay, so let's confirm that at t equals 7, let's confirm that the velocity did change sign. Okay, so the way to do that is look at the original velocity function. So this is the velocity, and really that 3 is there. So I'm going to rewrite it like this. Okay, so that's our velocity function. And then whatever makes the velocity 0, so we already found that, -1 and 7, we'll put on the number line, and then we'll do test points. So we'll plug in like -2, 0, and 8. So we're just testing points in between, from -infinity to -1, between -1 and 7, and then greater than 7. Yeah, so less than -1, between -1 and 7, and greater than 7. So I could have picked -3 or -10. Here you could have picked 2 or 3 or 6, and here you could have picked anything greater than 7. So, okay, so what we're doing with this is we're seeing on what intervals is this function positive or negative. Okay, so, and then the idea is that in between zeros, continuous functions are either always positive or always negative. So you can just test a single point. And so if you know at that point, at that test value, if the function is positive, that means it's positive everywhere in the interval. If it's negative, that means it's negative everywhere in the interval. So we just have to test one point. So let's plug in -2. So one thing, this 3 is positive, so we can kind of ignore it. Okay, we'll plug in -2. This factor becomes negative. This becomes negative. And so a negative times a negative is a positive. So that means at every point in time, when t is less than -1, this velocity function will be positive. Okay, plug in 0. So if you plug in 0, this is negative, and this is positive. Negative times a positive is a negative. Okay, if you plug in our last test point 8, this is positive and positive. And so positive times a positive is a positive. Okay, so what this is saying is that this function up here, whenever t is less than -1, this function is always positive. Whenever t is between -1 and 7, this function is always negative. And then whenever t is greater than 7, this function is positive. Okay, so we can see at 7, it did change direction because the velocity went from negative to positive. That was one of our things that we know had to happen in order to change velocity, or change direction. So this just means it was going left before 7, it stopped at 7, and then started going to the right. So that did change direction. Okay, so this first answer, I'll put it in the top right every time, is 7. Okay, for part B, they say a bug is moving back and forth on a straight path. Okay, the velocity of the bug is given by v of t equals t squared minus 3t. Find the average acceleration of the bug over the interval from 1 to 4. Okay, so in order, whenever they say average, some type of rate of change, it's not derivative, it's always slope formula. But when you want to find average acceleration, you're looking for change in velocity. Just like if you're looking for average velocity, you look in change in position. So kind of, as far as like kind of derivatives are concerned, it's kind of like earlier type functions, you know. So here I'll write that. Okay, so let's say, let's say just in general, let's say you wanted, just to kind of see it clearly, if you wanted average velocity, right, so that's change in position on the top over change in time. If you want average acceleration, like for this problem, you don't use acceleration function, you use velocity function. Okay, so that's what we use for this one, average acceleration. Okay, and we'll use the t-values at the endpoints of whatever interval, so we'll use 1 and 4. So to set it up, so it's v of, we'll say v of 4 minus v of 1, or 4 minus 1. Okay, so here off to the side we'll see, so v of 4, whoops, is 16 minus 12, which is 4, and then v of 1 minus 3, which is negative 2. So v of 4 is 4, v of 1 is negative 2, so that's 6 over 3, and so that's 2. Okay, so that's the average acceleration. So just remember, average acceleration, you're using velocity, you're looking at change in velocity over change in time. Average velocity, you're looking at change in position over change in time. Okay, so for C, they say the velocity of a particle for t between 0 and 9 is given in the graph above. Okay, which of the following values of t is the particle speeding up? Okay, so speeding up, we'll do it over here, whoops. Speeding up means the velocity is positive and acceleration is positive, or velocity is negative and acceleration is negative. Okay, if it was slowing down, either velocity is positive, acceleration is negative, or velocity is negative and acceleration is positive. Okay, so for speeding up, they have to I would say velocity and acceleration are the same sign. Okay, and then for slowing down, velocity and acceleration are different signs. Okay, so let's look at the graph now. So notice anywhere, so this is a velocity graph, so anywhere above the t-axis, so this stretch up here, the velocity is positive, and this stretch down here, velocity is negative. Okay, but so let's say we want to know when it's speeding up, we want to know where velocity is positive and the acceleration is positive. So notice, acceleration is derivative of velocity, and so the acceleration is positive anytime the velocity is increasing, right? So it's acceleration is derivative velocity. The derivative velocity is positive anytime velocity is increasing. So that means acceleration is positive anytime velocity is increasing. Okay. Okay, so that means like at this part here, the particle is speeding up. Let's write that. Okay, and then also notice down here, here the velocity is negative. In order to be speeding up, velocity could be negative as long as the acceleration is also negative. So notice, since velocity is decreasing here, so this whole stretch where velocity is negative and velocity is decreasing, that means acceleration is negative, so that those two parts will be speeding up. Okay, and just so you can see these other parts, this part here, velocity is still positive since it's above the t-axis, but since velocity is decreasing, the acceleration is negative. So that means for this stretch, velocity is positive, but acceleration is negative. So that would be slowing down. And then same with this part, this would be slowing down. All right, and then the quick way to tell, so you can, if you have a velocity graph, so this is just true if you have a velocity graph. Notice for these parts, this part here, these green parts, the graph is going, like away from the t-axis in both cases. So if from left to right, if the graph is going away from the t-axis, then it's speeding up. So notice like from left to right, this is going away from the t-axis. Okay, and then whenever it's going in towards the axis, so here it's going towards the t-axis, that means it's slowing down. Just like here, it's going towards the t-axis, so that means it's slowing down. Okay, so just to kind of summarize, so this will be speeding up. Okay, when t is between 0 and a little before 2, I'll just say 0 to 2, but it's a little before, say 1.8 or something. Okay, and then from 4 to 7, it looks like. All right, and then, so the only time, you know, at 4 it's 0, so it's not moving. So really t equals 5, and same at 7. 4 and 7, it's not moving. Seven's a little different. Seven's it's changing direction, but yeah, but really at 5 is the only time where right here the velocity is negative and the acceleration is negative at this point, so that means it's speeding up. Okay, so for the next one, for D, they say for t between 0 and 10, you have two different particles, P and Q, that are moving along the x-axis. Okay, the position of particle P can be modeled by xp of t, as shown in the figure. Position of particle Q is defined by xq of t. Selected values of xq of t, vq of t, and aq of t are given in the table. At what time t are the particles moving towards each other? Okay, so can you imagine if you're on a number line, there's kind of different scenarios of whether the particles are going towards each other, away from each other, or maybe they're just moving in the same direction, both in the same direction. But notice, like, in order for them to be moving towards each other, you're kind of two scenarios if you have two different particles. So you could have, like, this be particle P, and this be particle Q. Okay, and they're going towards each other. So think about all the things that are true at the in this scenario. So for them to be going towards each other, that means at a certain point in time, we'll say, like, let's just say at some point in time t1. So there's some point in time, call it t1, where the position of particle P at that time is less than the position of particle Q at that time. Okay, and that's this scenario, right? Position of P is less than Q, right? If this was on a number line, this value of the position would be less than this value of position. So P, because P is to the left of Q. So okay, so this is one scenario. So the position of P is less than the position of Q, and all this means is P is to the left of Q. Okay. Yeah, so position being less than means that particle is to the left of the other one. Okay, so this has to be true, but then also notice that the velocity of P, since P is moving to the right, that velocity has to be positive. So velocity of P at that same point in time has to be positive. Okay, and then since Q is moving to the left, that means the velocity of Q at that point in time has to be negative. Okay, so if all of these things are true, if Q is to the left of, or if P is to the left of Q, if P is moving to the right, and if Q is moving to the left, then that means they'll be going towards each other. Okay, all the opposite could be true also. So you could have, actually here, let me write this. This is P moving right. Whoops. And this one's Q moving left. So you have to like interpret all this stuff, right? You know, velocity negative, that means going left. Velocity positive, going right. Velocity 0 is it's stopped or at rest. Yeah, so you have to like interpret all this, you know, certain things. Okay, so that could be true, but all the opposites could be true. So you could have like Q over here and then P over here. So notice this is a situation where x of Q at some point in time is greater than x of P. Or sorry, less than. I don't know why I did that. Said that. Less than x of P. Okay, and then to go towards each other, that means that Q's velocity would have to be positive at that point in time. And the velocity of P would have to be negative. Okay, so one of those scenarios has to be true. Either this scenario here or this scenario here. Okay, so we look at these different points in time. You know, we only know particle Q. We only know things about particle Q at these 4 times up here. 1, 3, 7, and 9. So that's the only ones that we can test. We know more information about particle P. We know its position and velocity at every value between 1 and 10, but we only know Q at certain values, so we can only test those values. So we just go one at a time. So let's say at t equals 1. Okay, so at t equals 1, you can even draw a number line just to help us visualize. Okay, so at t equals 1, let's look at P. So t equals 1, the position of P is 2. And then at t equals 1, the position of Q is 4. So we have 2 and 4, and it's P here and Q here. Okay, and then let's see the at t equals 1. This is all at t equals 1. So at t equals 1, since at this point, since the graph of position is decreasing, that means velocity is negative. Okay, so that means that this particle here is moving to the left. Okay, and then Q, at t equals 1, the velocity is positive, right, positive 3. So that means that this particle is moving to the right. So they're not moving away from each other, or they're not moving towards each other, they're moving away from each other. Okay, so that's fine. So we'll test the next t value. Okay, t equals 3. Okay, so at t equals 3, you can see the position of P is 0, and the position of Q is 1. Got 0 and 1. Okay, P is 0 and Q is at 1. Okay, and then the velocities of each one. So velocity of P, since at t equals 3, since the position is decreasing, that means the velocity is negative. So this is going to the left. Okay, and then for Q, at t equals 3, the velocity is 0. So that means it's just standing still. Okay, so if one of them is standing still, then they can't be moving towards each other or away from each other, so it can't be that one. Okay, so the next time, t equals 7. Okay, so t equals 7. Looks like the position of P is about a half. And then the position of Q is -1. Gotta put the -1 over here and the 0.5 there. Okay, so this is the first one where Q is to the left, since Q is the -1, and then P is has a 0.5 position. Okay, so for P, particle P, so at t equals 7, the position's increasing, so that means the velocity is positive. So that means for P, it's moving to the right. Okay, for Q, the velocity is negative, so it's moving to the left. Okay, so another instance where they're moving away from each other. Okay, so it must be the last one is the answer, but let's just test it. Okay, so at t equals 9, the position of P is -1, and position of Q is -2. So -2 is Q, -1 is P. Okay, at 9, the position's decreasing, so the velocity is negative, so P is going to the left. Okay, for Q, velocity is positive at t equals 9, so that means the particle is going to the right. Okay, whoops, this one's velocity negative. Okay, so you can see, since like this, the velocity of the particle on the left is positive, and then the velocity of the particle on the right is negative. That means they're going towards each other. Okay, so t equals really just 9 as our answer. Okay, so seeing that, doing that for the first time would be super tricky, to be able to see that there's all these different cases that can happen, you know. Here, these are just kind of two of the cases. There's also a case where some of the, one or both of their velocities are zero. I guess that's kind of it. But yeah, but just kind of see that there's kind of totally separate scenarios. And, we're just looking for one of these two scenarios for going towards each other. So. Okay. Okay, let's go for that one. Okay, for question E, they say the position of a bug moving along a vertical post is given by the equation y of t equals negative 12 over pi times cosine pi t over 6 plus 6t minus 1. Okay, find v of 3. Okay, so this is, since this is going along a vertical post, they used y to represent position. But this is really just a position function. So if you want velocity, you just take derivative. Okay, so first we'll find v of t, and then that's just y prime of t. Okay, so I'll do it in steps. So if we're taking derivative of the negative 12 over pi cosine pi t over 6, so that kind of first term, we'll rewrite the constant. Okay, and then times derivative cosine is negative sign, but with chain rule you leave the inside alone, and then on the outside multiplied by the derivative of the inside. Okay, so derivative of pi t over 6 is just pi over 6. Okay, so all that's just the derivative of the first term because we had a chain rule. Okay, the next one, derivative of 6t is just 6, and then derivative of negative 1 is 0. So, okay, I'm just going to clean it up because we have to simplify this to be a number. So one thing, these pi's will cancel, and then the 6 and the 12 will cancel out to be 2 and 1. Okay, and then also those negatives will change to a positive. Okay, so this really becomes 2 sine pi t over 6 plus 6. Okay, so let's find v of 3. Okay, so if you plug in 3 for t, this becomes pi over 2. Okay, and then sine of pi over 2 is 1, so 2 times 1 is 2 plus 6 is 8. And that's the answer. Okay, for letter F, they say a particle is moving along the x-axis. The position and velocity of the particle is recorded for various times in the table above. Okay, at which time t is a particle moving towards the origin? Okay, so just to see what we're doing here. Whoops. Okay, so there's kind of two scenarios. So the particle could be to the left of the origin, moving to the right, so that would be going towards the origin. Or the particle could be to the right of the origin, moving to the left. So, and that would be going towards the origin. Okay, that's what we want. We want towards the origin. Okay, look at the situation on the left. The situation on the left is a particle whose position, it's at some time, I'll say t1, the position is negative. That's why it's to the left of 0. But the velocity is positive. That's why it's going to the right. Okay, so that's one scenario of towards the origin. The other scenario over here is the position of the particle at some point in time is positive. that's to the right of the origin. And then the velocity at that time, that same point in time, is negative. So the position is positive, but it's going to the left. Positive position, negative velocity. Okay, so let's see if one of the, and so notice what we really want. We want the position and the velocity to be different signs. Okay, so now that we know that, this actually becomes really easy. So now we can see they gave us the position and velocity at every point. Okay, so we can just look for where the position and velocity have different signs, and we can see at t equals 6, they have different signs, so that's the answer, t equals 6. Okay, letter G says the velocity of a particle is given in the graph above for values of t between 0 and 11. How many times on the interval does the particle change directions? Okay, so particles change directions when they go from positive to negative or negative to positive. When the velocity goes from positive to negative or negative to positive. So notice in this graph, this is a velocity graph. So all this time velocity is positive, and then all of a sudden it becomes negative, and then it goes to 0, but then it stays negative. So notice at 6, so this point here at 6, let me do a different color. So this is the only point where it changed directions, because it's the only point where before and after where the velocity was different signs. So you can see on this one, up here before 6, the velocity is positive, and then here after 6, the velocity became negative. So that means at 6, it must have changed directions. Change direction. Okay, and that's it. Oh, but this says, sorry, this says how many times did it change direction? Sorry. So at t equals 6, but then that's just one. That means it's just one time that it changed directions. Okay, letter H says the position of a bug moving along a straight path is given by that, so it's a position function. S of t equals t squared minus 2t plus 3. At what time t is the instantaneous velocity? So we want to know when the instantaneous velocity is equal to the average velocity on some interval. Okay, so instantaneous velocity is just velocity, which you could say is derivative position. Okay, average velocity is change in position. Over change in time. Okay, so we're going to do both of those, and we want to know when they're equal to each other. So we'll find the instantaneous velocity by doing derivative. We'll find the average velocity by doing slope formula, and then set them equal to each other and solve for t. All right, actually, I'm going to use here. Sorry, in this thing they used s of t, so I'm going to use s of t instead of x of t in this little formula. Okay, so so here we have position. So velocity is derivative position, which is 2t minus 2. Okay, and then average velocity on the interval is s of 6 minus s of 0, 6 minus 0. Okay, s of 6 is, let's do that up here. And then s of 0 is just 3. Okay, so s of 6 minus s of 0 is 27 minus 3 over 6. Which is 24 over 6, which is 4. Okay, so if we want to know when, so we've got an expression that represents instantaneous velocity, and then we know that the average velocity on the interval is 4. So we'll set those two equal to each other, and we'll find the time when they do equal each other. Okay, so that's the time. So that's the time when the average velocity equals instantaneous velocity. Okay, so letter I says the velocity of an object is graphed above for t between 0 and 10. What's the velocity of an object when the acceleration equals 0? Okay, so just to see what's going on. So this is the whole time when the acceleration is positive. Right, whenever the function's increasing is when the acceleration is positive. Whenever velocity is decreasing, that means acceleration is negative. So all these times the acceleration is negative. Okay, so what's the velocity of the object when the acceleration is 0? So think about it. If this is when the acceleration is positive and this is when it's negative, that means right up here is when the acceleration is 0. Okay, so right up here, acceleration equals 0. Okay, and that's really because the acceleration is 0, because acceleration is the derivative of velocity, and you can see the derivative of velocity is 0 because it's a horizontal tangent. Okay, over here, this can't really happen in the real world. Maybe at like the quantum level it can, I don't know, but not in like our world, our scale. So velocity can't just be constant, and then all of a sudden change to change from a negative value, a constant negative value, to a constant positive value instantaneously. It has to gradually change. It can gradually change very quickly, but it can't just instantly change from, acceleration can't instantly change from negative to positive in the real world. So, or at our scales, I guess. Okay, so there's only, so this is really at t equals 3. So really a of 3, when t equals 3, the acceleration is 0. Okay, so t equals 3 is that time that they're talking about. So they say, what's the velocity when the acceleration is 0? So when the acceleration is 0 is at t equals 3. And then we want the velocity at that time. Velocity at 3. And then the velocity at 3, since this is a velocity function, velocity at 3 is just the y value, which is 4. Okay, this last one's quick. They say the position of a bug moving along the x-axis is given by that. X of t equals at plus b, where a and b are both non-zero. Find the acceleration of the bug at any given time t. Okay, so we know for given position, we can take derivative to find velocity, and then take derivative of that to find acceleration. So we'll do that in steps. So velocity, Any time t is derivative of position. Okay, if this is the position function, derivative position is just a, whatever's multiplied by x. That's a constant velocity. Okay, and then the acceleration, you could think of it as the derivative of velocity, or you could think of it as the second derivative of position, same thing. Okay, since the velocity was a, derivative of that is 0, and so that's the answer. Okay, so the velocity is always 0 at any given time t.